Okay, welcome everyone to my continuation of what are my favorite theorems, a very biased collection as usual. Today I would like to talk about a theorem which is called the tree rotation bound. We'll see what that means. So tree rotations, and it's kind of very surprising in the sense that it's really small. Right? So there will be a number that is really large, and there will be a number that is really small. And it's kind of surprising how connected trees are, if you will. In a sense of different than connected from graphs, what you know. I will explain what I mean by how connected trees are. So if you like, for example, associations, so associativity, this will be it will apply for those as well. So it's kind of surprising how connected associativity is. But we'll see what it means. We start off kind of a little bit slowly. So what I'm looking at today is a little bit of a restricted notion, but anyway, we get a nice theorem, so let's just do it. It's called a binary tree. And a binary tree, or maybe more old-fashioned, an Ahnentafel. So here's my Ahnentafel on the right. And maybe this is more the classical picture of a binary tree. No, sorry. The right-hand side is a classical picture of a binary tree. But the left-hand side might be the one you have seen. You clearly have seen an Ahnentafel before. Anyway, I'm waffling. So a binary tree is really just the idea that you have a root vertex. So here's my little root. And here's my little root. Note that this one here is actually really a tree. It's drawn bottom to top, as a tree should be drawn. And for some reasons, the convention eventually switched. And most people draw nowadays trees top to bottom. So the root here is at the top in the left-hand side, which is a bit weird. Anyway, we go for it. So there's a marked vertex, a colored one, that I call the root vertex. And then at each step, you have one or two outgoing edges. Here, one or two outgoing edges. In this case, I have two. And here, so the branches, and here you have two outgoing branches as well. And okay, and then each thing that you see is again a rooted binary tree. So here's again a rooted binary tree. And here's again a rooted binary tree. Right? And, so it's kind of inductively defined if you want. Here's again a rooted binary tree. And here's again a rooted binary tree, which I defined by against the same process. You mark a vertex and you have a rooted binary tree and a rooted binary tree. I hope you get the point. It's not so difficult to define them. You can also just say each vertex you have two outgoing to the next layer or one outgoing to the next layer. So one outgoing or zero outgoing to the next layer as in this example. So both is fine. Okay. And yeah, let me waffle again that the classical one, the Ahnentafel, is, as far as I know, most of the time drawn bottom to top, as a tree should be. And then eventually people changed, and I don't know why, but nowadays I think drawing them top to bottom is like the standard convention. You also see them drawn left to right or right to left, or completely randomly in the plane or whatever. But I guess the most standard one nowadays is clearly this one. Anyway, we're clearly interested in binary trees, but we're not just interested in binary trees. We are interested in the tree rotation. This is really just taking your tree. Well, there's some vertex here, you want to rotate it. So you just rotate the tree over, right? You put this one, so exactly this operation. So you put this one down and put this one up, and you create a new tree, right? So do this operation on a tree that people call rotation. So rotation left and rotation right. And we can really think of it as like we're rotating around the vertex to the right, and what you get looks a little bit like this, but you kind of need to kind of take this part of a tree and put it on a slightly different position. Fine, that's what we do. And the reason why we do it, we'll see that later. But right now, this is operation. So we define an operation on trees called rotation, right? So left rotation, right rotation. And in words, a rotation at P moves P into Q spot, okay? And places Q, puts P into Q's spot and Q to the place where this is right child. And the childs are, of course, well, let's go back here, right? So childs, if you want, in that sense. So they're just the endpoints of a branching. Okay, so that's a really kind of easy rotation. So we put P into Q's spot, it goes here, and we put Q to where it's the other child. So that's a, what is it, the right rotation, right? And then the left rotation is defined similarly. And the other child is, of course, where if I rotate to the right, then the other child, I take the left one, and then the other child is the right. And of course, there's a left one as well. Anyway, so this is the idea of tree rotation. And you write them down. So here are all trees with 5 endpoints. You write them down and make a little like table. How are they related by tree rotation? Okay. And maybe you first want to just count the number of trees, and we just make it easy here. We want to count those number of trees, binary trees with n vertices. Turns out that the count is not really difficult. It's given by the Catalan numbers. So the Catalan numbers are those numbers that just appear everywhere. So if you go to the online integer sequence, Catalan numbers, you will see a sentence that says, this is one of the longest entry here, and rightly so. And absolutely, rightly so. The Catalan numbers count essentially everything. Kind of fun. But anyway, the only thing we need to know, there's an explicit description of the Catalan numbers, but what I really am interested in is the growth rate. I'm thinking of the case where n is really large and they grow really fast. So it's essentially 4 to the n. There's a correction term here. So like n to the 3/2, and there's a scalar which comes from applying Stirling's formula. But anyway, ignore the scalar, square root of pi. Square root of pi is fantastic, but you should still ignore it. So it's essentially 4 to the n. It grows really, really, really fast. Okay. And the question is, how difficult is this to relate the 4 to the n binary trees? There are quite a lot of them by rotation. So how many rotations do you need to get from one to any other? So what is the distance of that graph that you write down? So here's an example. You write down a graph and you wonder, what is the distance of that graph? And it has a lot of vertices. So you should expect the distance to be maybe not so small, but it turns out that it is actually. It's actually not even trivial to think of why everything should be related by a tree rotation, or what. So why don't you get something like a non-connected tree, right? So something like that, a non-connected graph, something like that. You don't. You always have a connection, and I will ask the question, what is the distance, the maximal distance between them? How many rotations do we need to go from one binary tree to the other? And I say it again, we have this ridiculous number of binary trees, so we should expect a quite large number of rotations. And turns out that you essentially need no rotations at all, okay? 2n minus 6, n is the number of vertices. Compare this to this crazy function, which just outgrows it, this is a log plot. Even in a log plot, it will outgrow that function by, so one of them is linear, and the other one is exponential with the exponential, essentially exponential with the exponential factor being 4 to the n. And this is like ridiculous. Here's another example. So all of these are tree relations. So here n is like 4. Yeah, I'm counting the endpoints here. So 2n minus 6 is then 8 minus 6 is 2. So the maximal distance should be 2. And indeed, it's 2. I can go from this one to this one, for example, in 2 steps. And this is just, I mean, this is just really amazing. I think this is absolutely fun. So this small number is the answer compared to this number of vertices of that graph. So the graph is actually pretty kind of connected in a certain sense. So trees are very connected by tree rotations. And where does this all come from? This really comes from the associahedron, because if you just think of trees as being ways to bracket a sentence, maybe let's do that here. So here, for example, this top tree corresponds to bracketing A, B, C, D according to the branches. So something like this, right? So A, B, C, D. So every tree here corresponds to a bracketing. And you can think of a bracketing and you can ask, what are the associativity moves that I need to apply? And I write down a graph. Well, whenever an associativity move gets me from one neighbor to the other, I write down a graph, and that graph is called associahedron for any number of vertices. And you ask the question, how connected is that graph? And it's exactly the answer from before. And it's just really ridiculous, again, because the number of brackets you need, the number of terms, the number of ways you can bracket those is really large, but you can go from one to the other in using an associativity move. So let me just write it down in case you have forgotten what an associativity move is. It's, of course, this one. You can use those moves, and you only need, at most, this number of moves, which is really, really tiny, to go from everywhere to everywhere else, which is ridiculously fantastic. Anyway, I hope you enjoyed this video about how connected trees are. I hope it makes some sense now. This is a very small number compared to the Catalan numbers, which is 4 to, let's say Catalan numbers are 4 to the n. Yeah, I think this is a pretty cool theorem. That's why it's on my list. So I hope you enjoyed this video, and I also hope to see you next time.